So, hello everyone. Good morning, good afternoon, or even a late good evening, wherever you are. This is the International Space Sciences Institute's Game Changer Seminar Series, and I'm Tilman Spohn, and I'm again your host today. In the series of these 10 talks in the first quarter of this year, we're looking at habitability from galactic to microbial scales. And today, we have a talk on a much quoted concept of the circumstellar habitable zone by Professor David Catling. And the title of his talk is The Habitable Zone Hypothesis, A Critical Look, which is, I think, what we all need to take. While for the habitable zone, the stability of water is essential. We will next week have a talk on what else is needed in addition to water. And then a week thereafter, a talk on how life may itself shape habitable conditions. By the way, if you want to follow our seminar program and other easy activities, consider subscribing to our newsletter. You can do so at the bottom of any of our web pages. Now, David is a professor in Earth and Space Sciences at the University of Washington in Seattle. And he's well known as a planetary scientist and as a geo and astrobiologist whose research deals with planetary habitability, including how the environment and life on Earth co-evolved over billions of years. He's been involved in NASA's Mars program and astrobiology research, for example, being on the science team for the NASA Phoenix lander and the Perseverance rover. In addition to his many scholarly papers, he's written 2 books in the past decade. One for the layperson, Astrobiology, a very short introduction. I read it, and it's great. And for researchers with Jim Casting on atmospheric evolution on inhabited and lifeless worlds, which is another great book. So with that, David, the floor is yours. But before I give you the floor, just let me say that following Dave's talk, there is, of course, the question and answer. You can write your question in the chat, in which case I will read it to David. Or you can raise your hand using the raise hands tool on Zoom, and then you can speak yourself. So David, now the floor is yours, and we're looking forward to your talk.
Okay, well, thank you, Tilman, for the invite to talk. And Tilman specifically asked that I talk about the habitable zone. My sort of general interests are in the air and the surface of planets and how life can affect the dirt, the rocks, and the air. And increasingly, we know from the Earth sciences that atmospheric composition and climate have controlled or modulated the tempo of biological evolution, while there's a feedback because biology modulates the composition of the atmosphere. So it's a coupled system. But certainly a central concept is the habitable zone. And I want to just start by sort of giving you my take-home messages so that if your mind wanders, then at least you know what I was going to talk about. And then also I'll come back to this and it will make more sense once I've been through my talk. But the habitable zone, or liquid water belt, as it was once called, as I'm sure you know, is just the range of orbits around a star where liquid water can be stable in principle on a planet's surface, particularly a rocky planet's surface. But it's a hypothesis. And I tend to think of it also as a probability. It's a probability of an enhanced probability of life on a planet's surface across some range of orbits. But you can also think of it in terms of Bayesian probabilities. It's a sort of best estimated probability given all prior knowledge of habitability and therefore possible life given that particular context of a planet-star distance. But the other important point is it actually relies heavily on our understanding of Earth. So the conventional habitable zone relies on the idea that there's a stabilizing feedback, a negative feedback of Earth's carbon cycle on the climate system, so that you can, as you go out from a star, the climate will stabilize at a higher carbon dioxide level. But I think, planets could be very different in all sorts of ways, and this could confound the hypothesis. You could have planets in the habitable zone that are not habitable. Maybe they're really small, like say the size of our moon, and so they don't have an atmosphere. Or maybe they're really big, and so they hang on to a very thick hydrogen-rich atmosphere where it's crushingly hot, crushing pressure and extremely hot at the surface. Or maybe it's a planet that migrated in, and so it's different from what you might expect. And then the final point is that it's eventually testable, but it's not easy. And so it really requires one of these next generation telescopes beyond the James Webb Space Telescope that can measure atmospheric composition trends within planet-star distance. And that also, apart from requiring a big telescope, also requires a big sample to test this hypothesis. So to get to those sort of broad messages, there are various steps I'm going to go through. And part one is just where this concept came from, the habitable zone. Part two is about thinking of the habitable zone as a probability distribution and in a Bayesian probability framework. And then part three is getting a bit deeper into this idea of the carbon cycle and the habitable zone. So I'll give some background on the geologic carbon cycle and how that plays into this. And in some ways, that's with apologies to vegans, that's the meat of the talk with some interesting results. And I'd like to acknowledge up front the people that worked on me with this, which are my former PhD students, Josh Curzanson-Totten and Owen Lima. So where did this concept come from? Well, as far as I know, the first time it was alluded to was by Isaac Newton in his Principia. So that's all the way back to the 1600s. And he just noted that water, if you're out at the orbit of Saturn, would be frozen. And if you're at the orbit of Mercury, it would just boil away or evaporate away. And this was how he was explaining Earth's special position. Now, why exactly he chose Saturn rather than Jupiter, I have no idea, because he doesn't explain that. So he has a very wide habitable zone for some reason, but he doesn't explain his thinking behind that. And then William Whewell, another Cambridge University person, in his book talked about a temperate zone between a central torrid zone and an external frigid zone in the solar system. So he introduced the word zone, if you like, which was later taken up. And then Harlow Shapley, who was an astronomer at Harvard, who discovered the size of the Milky Way, that's his most famous contribution, in the 50s talked about the liquid water belt, not as close as Mercury, nor as remote as Jupiter. That was how he defined the habitable zone. And then finally, the actual phrase habitable zone was introduced by Sushu Huang, a Chinese-American astronomer then at UC Berkeley. And he actually defined it in a sort of somewhat modern way. A planet is habitable if its distance from a star satisfies a certain range of distances. And even in his kind of follow-up popular piece in Scientific American, he even had a diagram which looks a bit like the diagrams of the habitable zone that you find in modern textbooks. It's not exactly clear how he decided on this, but it looks like he decided the habitable zone for the sun would be, from Venus to Mars, and then he scaled to other stellar types, which are indicated here based on insolation. And then you get to the 70s, and Michael Hart introduced the idea of a continuously habitable zone versus a habitable zone. So habitable zone just refers to an instant in time. So the sun on the main sequence, as it ages, gets brighter, roughly 10% per billion years. And what it means is that the habitable zone is gradually, slowly but surely moving outwards. And of course, it was more inwards in the past, as illustrated in this diagram here. And so the continuously habitable zone, according to Michael Hart, is that in which a planet could remain habitable for some period. So one could talk about 4.6 billion years for the solar system, or one could talk about the whole main sequence lifetime. Okay, and that in a modern context is important when we get to red dwarfs, M stars. So for example, this is a diagram from my colleague at the University of Washington, Rory Barnes, for the planet which is around our nearest star, Proxima Centauri b, in the habitable zone. Well, it's in the habitable zone today, as you can see on the graph, but because red dwarfs take a long time to settle down into their main sequence and they're superluminous to begin with for a few 100 million years, then it used to be within the habitable zone and it used to be baked. So there's a big question as to, did this end up as just an evaporated core of some planet that used to have an atmosphere, so it doesn't have one anymore? Or did it go into a runaway greenhouse? Is it Venus-like? Did it get stripped away and then the atmosphere came back? So we really don't know any of these things, but it's an important concept that the habitable zone moves, and it's less important for sun-like stars, but is important for red dwarfs. Michael Hart's papers were also the first ones to sort of think a bit more about applying climate models to define the habitable zone. But his papers are a bit bizarre because they calculate a very narrow continuously habitable zone around the sun, just from 0.95 astronomical units to just over an Earth-Sun distance of 1.01. And he sort of concludes, this is a very narrow continuously habitable zone. And the way he did his calculations, it was even narrower around other stars. And he ends up arguing that life is unique to Earth in the galaxy. But his model was wrong. And that's because he assumed that if you went to the outer habitable zone, you would just snow over and you'd be trapped forever. But of course, volcanoes can poke through the ice and they can spew out carbon dioxide, and that can build up and that can melt the planet. In fact, in Earth history, we have evidence of possible so-called snowball Earth events when ice extended down to low latitude for several times in a couple of periods at the beginning of what's called the Proterozoic eon and at the end of the Proterozoic eon. So that's 2.5 billion years to 541 million years ago. That's the Proterozoic. And evidently the Earth got through those events because while we're here, life continued. And what he didn't realize is that this stabilizing feedback in the carbon cycle, where if it gets too cold, volcanic CO2 will build up, and if it gets too hot, it will be drawn down, at least on a planet that operates like the Earth. So let's talk about that a little bit more. So the kind of idea is that on 1 million year timescales, roughly, atmospheric carbon dioxide is controlled by a balance of carbon outgassing and then also losses of carbon dioxide through weathering. So it dissolves in rainwater and it reacts with rocks. It releases cations like calcium, and then you can make calcium carbonate that precipitates in the ocean. And you can say, well, this sounds like a nice idea, but is that what's actually happening? And there's various ways to approach this. You can come at it from the geochemistry, or you can just do a sort of thought experiment. But anyway, on the lower right is a thought experiment idea, which is taking what we know about carbon dioxide outgassing, our estimates from volcanoes, and also what we know about weathering rates. Let's suppose we just sped one of those up by 25% so that it was in imbalance. And if you do that, well, very rapidly, the Earth will either, in one case, accumulate a massive amount of carbon dioxide, or it will become extremely cold because we'll lose it as into the weathering sink. So there has to be a sort of CO2 police, which is why I've got this policeman up here with his donuts and his radar gun, policing carbon dioxide. And this police is actually, what I mean is just this weathering balance of CO2 outgassing. And that was first proposed in detail by a paper by Walker et al., 1981. And so you can estimate fluxes, that's what the F's are in this equation, which depend on the amount of carbon dioxide relative to modern, and then some temperature dependence as well in a sort of Arrhenius type of law. And this paper is much cited, both in the Earth science literature, but also planetary literature as well, because this is how Earth-like planets are thought to work. But there's a few more nuances, because there's not just this continental weathering, you can also have seafloor weathering, and we could observe it in drill cores of the ocean floor. So there's not just laminated sedimentary rocks in the ocean. If you look in the basaltic seafloor, you'll find calcium carbonate veins and crystals. So calcium carbonate's also, or the carbon dioxide is also being removed into the seafloor, but it's not so important on the modern Earth. But if you pumped up the temperature of the deep ocean, you would get calcium released in water rock interactions from the seafloor, and you get a lot more seafloor weathering. And so we think in the deep past of the Earth, this may have been a more important issue when you had more seafloor spreading, and when you had episodes of warm temperatures, such as the late Cretaceous, for example, when there were dinosaurs roaming around in the Arctic, for example. But this is also built into this concept of the habitable zone. There are two assumptions buried in here. One is that it assumes a CO2, H2O, Earth-like greenhouse effect. And it also assumes that there's this stabilizing feedback. The basic idea is that if the temperatures are to creep up and it becomes hot, you have a bigger hydrological cycle. You have more weathering, because they're temperature dependent, weathering rates. And so you have the loss of the CO2, and then it will draw the CO2 down. Conversely, if it's really cold, the weathering declines and the outgassing goes into imbalance and builds up the CO2. And as I just talked about, this has to be right for the Earth on 1 million year timescales. Otherwise, the Earth would get out of whack. And in principle, then, you can test this hypothesis, because it means that as you go across the habitable zone, as you go outwards from a star and the sun or a star light gets fainter, CO2 should go up. So there should be a trend of carbon dioxide increasing as you go throughout the habitable zone. And we can build models of this kind of thing, because we have information about how these weathering rates vary, how the continental weathering rate, the seafloor weathering rate, they have different functions. The one on the seafloor depends on the deep sea temperature and the pH, so not quite directly on the CO2 as the continental one does. And we can use broad empirically based literature to try to get these uncertain parameters that are in here. And my group has written 4 papers so far, using a model which we first developed back in 2017 and applied to the last 100 million years of the Earth. And then we applied it to the last, well, basically the whole of Earth history. And we've also applied it to the habitable zone, which I'll talk about later. So this is the idea then, is that within the habitable zone, your carbon dioxide level will increase through this stabilizing feedback. And here's the Earth at 1 relative stellar flux unit. But of course, the habitable zone, or the stabilizing feedback, breaks at either end in this carbonate silicate cycle. And at the inner edge, the most drastic break is that you go into a runaway greenhouse effect, where it's so warm, water vapor builds up a lot in the atmosphere. It basically blocks the infrared radiation coming from the surface. And so it'll only let out the infrared radiation at a fixed rate, fixed by the physics of water vapor in the upper atmosphere. The Earth then behaves like a sort of infrared, or the Earth's atmosphere behaves like an infrared photosphere, radiating at a fixed rate. And if more sunlight's coming in than infrared is going out, that's a bad situation, because the temperature just keeps going up and up until the surface melts. And in the meantime, you lose your ocean to space. So that's the runaway greenhouse effect. And then at the other end of the habitable zone, if you try to pump CO2 up too much, CO2 is a very good Rayleigh scatterer. So the sunlight coming in will be scattered out to space, and you can't really, you get sort of diminishing returns from the greenhouse effect. Another possibility is that the CO2 starts to condense out at the colder temperatures and forms clouds and deposits on the surface of the planet. So outside of the habitable zone, at least today, we have Mars, well, depends. Mars is, whether Mars is in the habitable zone or not, depends partly on other factors, such as the size of the planet. But it happens to be a small planet, half the diameter of the Earth, and it's not able to maintain a carbonate silicate cycle. And then we've got Venus on the inside, which is a clearer cut case. Now, Jacob Bean, in a paper back in 2017, proposed verifying the habitable zone. So that was their idea, by looking for this CO2 trend. There's been a lot of work on defining where exactly these edges of the habitable zone are. And so you'll see papers like this one by Koparapu et al., where they run a different climate model and they get different edges from, say, a previous model by Frank Celsus, because they've updated something in the radiative code. But mostly these calculations are done with radiative convective models, maybe 1D, sometimes 3D GCMs. Relatively few are done with carbon cycle models. But a typical habitable zone width, anyway, from these kind of calculations is something like 0.95 out to 1.7 astronomical units, which you're probably familiar with, nice colorful plots like this one from Sunny Harmon at NASA Ames. And this one's populated as well with some exoplanets, albeit ones that are around fainter stars than the sun. And you can also define the edges of the habitable zone depending upon your assumptions, whether you have to have a runaway greenhouse effect or what's called the moist greenhouse effect, which is this kind of a pre-runaway stage where planets lose their atmospheres to space rapidly, which is the more, well, it's a different limit in this case. Or you can assume things about the solar system. So maybe Venus was habitable up until 1 billion years ago or something, and that can shift your habitable zone edges. So there's lots of debate in the literature about where exactly the habitable zone edge sits. And I'm not going to talk about that because that's not work that I've done. Instead, I'm sort of interested in the carbon cycle assumption. And I've said this is the American expression, a look under the hood, or in the British English, a look under the bonnet of doing research. And so when I saw Jacob Bean's paper, I sent an email to my student, which is here, saying, okay, Jake has proposed that we can look for this CO2 trend, but nature's usually not as simple as that. There's all these possible permutations we could think of for a planet about volcanic outgassing rates. And maybe that set point of a thermostat could vary widely. The PCO2 could vary widely depending upon how much land there is on a planet or different parameterizations, different greenhouse gases. So what could we get out of our carbon cycle model for those kind of conditions? And would it not look like this assumption here, but instead just be a mess, a scattered mess? Or would we actually see something that looks like our conventional habitable zone in reality? So I'll talk about that in part 3 of my talk. But now I'm going to move a little bit to a different but related subject about finding life on exoplanets, which of course is what we want to do with the habitable zone. And this gets to my point that the habitable zone is a bit like a probability distribution for where we might find life. And I started thinking about this when I attended a NASA-sponsored workshop in 2016. And we were asked to consider, suppose life is detected, let's say in the 2030s, and it makes the front page of the newspapers. So here I've got, a fake New York Times front page, evidence of life found on an exoplanet. And then because, you can contrast that with a tabloid, and Britain has the most scurrilous tabloids in the world. So I've got one of those. Aliens are out there beneath royalty handbags. And the question is, how would we assign kind of uncertainty to this? Often when we think about how life might be detected, it's not going to be definitive with, say, biosignatures, which are atmospheric gases, which we think are biogenic. So I normally prefer a quiet life of cups of teas and petting cats, reading books, but I must have stepped out of the room because somehow I got the job of leading a paper to address this issue. And the issue was, have we found life or have we found a false positive? And here's a planetary scientist wearing a mask, which has happened a lot recently, and looking at a planet and thinking about this issue. And there's a good reason to think that the way to approach this issue is some kind of Bayesian statistics, because that's the correct approach, I believe, of dealing with probabilities when there's an incomplete set of information, which is always going to be the case with exoplanets. And we should not disregard our knowledge or previous experience when deciding whether a planet has life or not. So we should not disregard what we think about, say, a habitable zone. And so I just wanted to talk a little bit about applying this to exoplanets, but let's just start at the beginning with the Bayes hypothesis. And the idea is that if you heard some hooves behind you, you wouldn't think of a zebra as being the thing that's clip-clopping along, because, well, horses are more common. So you use your prior knowledge in daily life, and Bayes' theorem is just putting that into mathematics. And it only depends on three things. So it's not that complicated. There's a prior, which is the hypothesis credible to start with, some probability of that. You multiply by the likelihood. If the hypothesis were true, what's the probability you'd see the evidence you see? And then you divide by the commonness of the data amongst all. So if a symptom of life on a planet is common to both inhabited and lifeless worlds, all planets, then a big denominator will shrink your credence in the hypothesis of life alone. If a symptom is rare and special, then your credence increases. So we believe a hypothesis to the extent that it's credible to start with, that it's consistent with the available evidence, and that the evidence is uncommon amongst all. That's basically what Bayes' hypothesis mean. And we write things like this: the probability of hypothesis given the straight line, the evidence. And this is Bayes' theorem. So to apply this to exoplanets, we have to think in terms of context. So we have the probability of life given data and context. And maybe we have some context which might be an Earth-sized planet, an Earth-sized mass in the habitable zone of a G star or something. That's our context. So we can define context how we want. After some algebra, starting with Bayes' theorem, we end up with this equation, which basically has the posterior probability we seek, the probability of life given the data and context. And it's a function of the likelihood of seeing a data from a planet with life and the likelihood of seeing, basically the data with no life and the same context, and then some prior probability of life given the context. And the habitable zone then falls into this kind of prior probability, because that's one way of thinking about where life might be for the exoplanet. Of course, there's a lot of information that goes into this idea. We've got the context, we've got the data. In the middle, we've got planetary models, which can help with these likelihoods, and in particular, the possibility of a false positive. And then we've got prior knowledge, which is essentially all of our astrobiology, the factors that influence habitability. And then we put those all together, and we'll have some probability in the end of life given the data and context. Quantities such as the average probability of life on an exoplanet are quantities that emerge from integrals. So let's suppose we wanted to find the average probability of life on a particular context of say, stellar type. Then we'd have a prior of life given the context. And then from astrophysics surveys, we know the probability of, say, a G star, which is 8%, or the probability of an M star, which is 76%. But we don't know much else, because we know that the probability of life given G stars is greater than 0 because we're here, and probably the probability of life given O stars, which don't last very long, is going to be 0. But apart from that, we don't know much, and all of this is things that we need to learn in the future. But of course, we can update our priors as we get more knowledge coming in. And in particular, the habitable zone can be thought of as being related to this Bayesian prior, the probability of life given context. So if the habitable zone looks like this, then if you were to plot out the probability of life given context, perhaps it might look like this, where we're following the picture here for sun-like stars, where we've got some higher probability of life in the habitable zone. In the middle, where it's too hot, then it's lower. But is it zero in here? Is it zero on the outsides? All of these things can be debated, because maybe we could have more arid worlds that can't do a runaway greenhouse effect interior to the conventional habitable zone, or we can have greenhouse gases like hydrogen on the outside of the habitable zone that support planets. And what, in any case, is this probability value in the middle? So this is, but this is still unknown, but I think it's useful to think about this context, because in the long run, what we want to do is try and put numbers on things and turn somewhat qualitative ideas into science. So let me now talk about the carbon cycle and the habitable zone. So this is the idea that you've got this stabilizing feedback, and it's allowing the habitable zone to be the extent it is by raising the level of CO2 as we go out for an Earth-like planet behaving in an Earth-like way. Imagine then if we wanted to keep a planet's temperature constant as we go out from a star in the habitable zone, what would the curve look like? So if we have incident stellar flux normalized on the x-axis, and we have carbon dioxide on the y-axis, as you increase the carbon dioxide in logarithmic space, the surface goes up, temperature of a planet goes up linearly. That's true for the modern Earth for small perturbations. Up to about, once you get up to about 0.1 bar, the radiative transfer gets a bit more complicated, because weaker CO2 bands become more important. And so it starts to deviate from linear. And if you had a perfect carbon cycle negative feedback, it would keep you on this curve, so to speak. So that's the idea. But in reality, you probably don't have something which is a perfect feedback. And that's partly simply because of the way the geochemistry works. So to actually put numbers on this thing rather than have a sketch, here's a calculation. So here's the line where we keep the Earth, let's imagine moving the Earth out and keeping its surface temperature at 289 by fiat. Then it would follow this curve here. But and that's not the case, we're not actually imposing a carbon cycle model, we're just saying what level of CO2 do we need? So it's kind of like the thing that people do to define the habitable zone edges, where they do it with a radiative convective model or something. But let's suppose we run a carbon cycle, which we did here, and we vary things in it, which we don't know very much. In particular, the weathering dependency. Remember, the continental weathering depends on PCO2 to some power, and the weathering also depends on temperature to some exponential factor. What happens is that typically in the carbon cycle models, as we go out in the habitable zone, because the carbon dioxide level is being raised in feedback, that also affects the weathering because it's CO2 dependent. And you can achieve carbon balance about gassing and loss of the carbon at cooler temperatures as you go out, which is this contour plot here. So in other words, it is a moderating feedback, but how good it is depends on how the carbon cycle operates. And if it's a weaker carbon cycle, you'll get cold as you go out. You won't stay at a fixed temperature. And so this is an example of just one of the ways in which the system doesn't behave necessarily as simply as one might think. Oops. And then what we did is there are all these factors and parameters that go into the carbon cycle that we can vary, such as how say how biology might affect the weathering or what the land fraction is relative to ocean. Because obviously if you don't have any land, then the only weathering you can do is on the seafloor. Or if you have very small amounts of land, then it will be dominated by the seafloor. If you have large amounts of land, it'll be dominated by continental weathering, which operate differently. So if you randomly sample all of these factors, and you do a Monte Carlo run, then you end up with stable climates. And those tend to cluster along the habitable zone, so which is running along the middle here. Obviously, if you're too hot, you'll go into a moist greenhouse and lose your ocean. And if you're too cold, you freeze over. The sort of global mean temperature, roughly speaking, where you freeze over because there's a latitudinal dependency, is actually not 273. It's a Kelvin. It's a bit lower than that, around more like 248 Kelvin. So this is what you get. And this color scale here shows the relative point density. Now, if you impose a sort of naive straight line fit, why not? We like to do straight line fits. You'll find that the R squared value is 0.5. So only half of the variance explains this quasi-linear stellar flux log P CO2 relationship. All of the rest of the scatter is just the vagaries of the carbon cycle. And there's something else going on here, which is that we also have these limits of frozen over versus you lose your oceans. So there's almost a sort of predetermined effect here that you're going to have some kind of zone anyway, just based on those limits. And what really shows the negative feedback here is really the clustering of stable climates in the middle of this plot. And so what we wanted to do was see, well, can we detect that? Because you might get a bunch of randomness scatter going on that doesn't really, is just the vagaries of the way planets work and doesn't really define this negative feedback per se that we have as the basis of the habitable zone. So we can talk about the probability of how you might just randomly get this distribution versus, or rather have a uniform distribution here versus this different distribution due to the negative feedback. So if you look at that issue, here's the probability on the y-axis that the observed planets match just a sort of log uniform distribution. And then we want to get away from that and to match our actual distribution due to a negative feedback. And how many planets do you need to observe before you get there? And it turns out that to do that, you actually need a lot of planetary observations. And what we're doing here is imagine you have a telescope, imagine you're looking at the CO2 level through atmospheric spectroscopy. You also know the planet star distance. And also we're looking at in this case, because that's what we did the modeling for, we're looking at a sun-like star. Then you're going to need a lot of planets. And basically the current concepts that are being looked at are things like, they're called the HabEx, which is a Habitable Exoplanet Imaging Space Telescope, 4 meters mirror. LUVOIR, which is a large UV optical infrared telescope. There's some different concepts there, one with a big 15-meter mirror, another one with an 8-meter mirror. And these are the estimates for these kind of concept missions for, how many planets would be studied, Earth-like planets. And so we basically would need about 80 or so planets to be observed and for their CO2 to be measured to have some chance of actually, all we're trying to do is just verify the hypothesis of the habitable zone. And it turns out to be really quite tricky because you need these big telescopes and you need all this amount of time to get the observations. And we haven't even got into other problems here, which is we could have unearth-like planets. So ones that are perhaps a lot bigger, maybe they've held on to their hydrogen-rich atmosphere. There is always the problem in climate models of what we assume about clouds and albedo effects, and we could be confounded on that. Other greenhouse gases, some people consider methane. I think it's relatively hard to produce methane on an Earth-like world abiotically, but that's another talk. The bottom line, though, is that even the conventional habitable zone concept requires to verify it, going back to this paper by Jacob Bean and our follow-up with the carbon cycle modeling, requires a big telescope, something that we're not really thinking about until maybe the 2030s. So these are my take-home messages. By the way, I've left plenty of time for talk because I have to leave just shortly after the top of the hour because I have to give a lecture for a class after this. So I've timed this to finish a little on the early side. So we've got a hypothesis and a probability. That's what the habitable zone is. This enhanced probability of life on a planet's surface across some range of planet-star distances. And how exactly that works, what the actual probabilities are to be determined. I don't think we really know. At the moment, it's a somewhat qualitative probability. But what it does rely on, at least this conventional habitable zone, when I mean unconventional, I mean, say, using different greenhouse gases, such as hydrogen, which is not how this concept came about. It came about with respect to the Earth and its neighboring planets, which are can be thought of in terms of CO2, H2O, greenhouse effects. So the habitable zone relies on this understanding of Earth's geologic carbon cycle, and it assumes this negative feedback. But this negative feedback depends on all sorts of things that are intrinsic to a planet, because all planets are, if you like, individuals. They're not so easy to understand on a spectrum as, say, stars are, because of all their different ways they can vary. And so the way that planets vary can scatter this nice idea of a simple trend into a whole bunch of scattered points, although there could be some general trend that is more probable that you will end up having a negative feedback distribution. And then finally, if we look into this in a bit more detail, it's actually quite difficult to prove the habitable zone hypothesis, that there will be this trend of climate as we go out. And we're really looking to the future for that, for something like the next generation big mirror telescope in space beyond James Webb Space Telescope. So that's it. Thanks very much for listening, and I'm open to questions.
Yeah, thank you very much, David, for this fascinating talk. There are questions already in the chat, and I begin with Jean-Pierre de Vera, who touches on something that actually I think you already answered to some extent, because he's asking, you're basing your models on CO2, but there are other greenhouse gases like hydrocarbons and methane, and how would things change if you included those? You want to comment on that, or?
Yeah, well, I mean, David Stevenson from Caltech wrote a paper in 1999 arguing that you could have free floating planets in space. They don't even need to be around a star if they have a thick hydrogen atmosphere and enough internal heat, geothermal heat, that you could even have a planet that's habitable, just floating out there in interstellar space. Well, then there is no habitable zone in that case. But I think the problem with those kind of ideas is that they're hypothetical at the moment, and it's useful to work with what we know, right? If you think in Bayesian probability terms. And what we know is that we have a planet like the Earth, and it works with this negative feedback system, and it's been doing it for a long time, 4.5 billion years. And we also can see how carbon dioxide based systems have failed on our neighboring planets. On Mars, where you have extinct volcanoes, you don't have the outgassing, you don't have the liquid water at the surface to make the cycle operate. And on Venus, where it's gone into a runaway greenhouse effect. So if you go back to where this came from originally, that was essentially the concept of people like Harlow Shapley and Huang, that they were looking to the solar system as being these are things we know, these are our examples, this is how it works here. But there could be hydrogen-rich atmospheres where there's enough hydrogen that the surface is warm. It's just that we don't have examples of rocky worlds like that in the solar system. And it depends on how those things actually arrive at where they end up. Because when we look at exoplanets, I mean, obviously there are things like super Earths or sub-Neptunes and so on that apparently look as though from their bulk density, they do have these thick hydrogen and helium envelopes, but often these are so massive, the estimates of these atmospheric envelopes are so massive that the temperature at the surface would cause rock to melt. So obviously those planets are not habitable. The question is, are you going to end up with some thinner shell of a hydrogen-rich atmosphere that supports liquid water on the surface and therefore life as we know it? And I think we just have to wait and see whether we're able to detect in the future those kind of planets. But those would confound the habitable zone, and they're not the conventional habitable zone. They could exist beyond the orbit of Mars. Whether they exist in reality or not, I don't know. In principle, they could. And how exactly, what's an interesting question is how exactly those planets would work in terms of their cycles, in terms of maintaining life, because they're so different to what we know from the Earth.
Yeah, fascinating thought. The Frank Muller-Karger asks, outside the extremes in temperature, radiation, could you include life itself, photosynthesis, respiration, in how you modulate the carbon cycle and other gases? It is not just weathering of rocks, adding bio to geochemistry. So basically the feedback of the biosphere into the carbon cycle, if I got it.
Yeah, so that's a reasonable question. On the Earth, it's, the heavy lifting, if you like, is done by the inorganic part of the carbon cycle, because if you just think about fluxes of carbon from outgassing and then deposition, about 80% of the carbon is going out as carbonate minerals, and only 20% is going out as organic carbon in the sediments. So it's dominated by the inorganic part of the cycle, and certainly that's the only thing that could be going on before life originates. The effect that life has, at least it's thought, on the carbon cycle is mainly through this effect of enhancing weathering, because there's data on that. People have looked particularly at vascular plants and trees and their root systems, which maybe enhance weathering by up to an order of magnitude. So those kind of effects are definitely important. Now, if you had a different something else, some kind of different balance on another planet, where somehow photosynthesis is more efficient at sucking out the carbon than it is on the Earth, because we don't really understand, I don't think, why we have exactly this balance between organic carbon and carbonate carbon on the Earth. And maybe if it were different on another planet, it could be more strongly modulated by biology. But a lot of what photosynthesis and respiration do is just a cycle that's imposed on top, that's sort of zero sum. So a lot of the modern biosphere, in the summertime, it makes a lot of organic carbon, and in the wintertime it disappears. And so we just have a sinusoid. And on the long time scales, the thing that really matters is the geologic cycle. And there we're talking about sources and sinks of carbon, the source being outgassing and the sinks being what goes into the sediments. So it would have to affect that geologic cycle in a big way.
Okay, Jerome Benedict asks, thanks for the great talk, but is water the only liquid with life-creating potential? Is being a liquid on a rocky planet mandatory?
Well, this is another part of the conventional in conventional habitable zone, right? That we are just assuming that it's life as we know it, and therefore life as we know it requires liquid water. There is a literature on other potential solvents, such as liquid ammonia or hydrocarbons, but they have their problems. Let's take liquid hydrocarbons, since people talk about this for Titan. On Titan, the low temperatures that produce these liquid hydrocarbons and the chemistry of the system means that it's it's actually not a very good solvent. And basically, we already know from this kind of petrochemical literature that it's very hard to dissolve large molecules in something like liquid methane at Titan-like temperatures, for example. And my belief is that you need large molecules for life, because a fundamental aspect of life is having a genome. I mean, if you don't have a genome, you're not alive. You can metabolize like a car, but the car doesn't have a genome and self-replicate. Unfortunately, my car doesn't self-replicate. And you need a big molecule to encode the information, a recipe for an organism, which is a genome. And when you look at these alternative solvents, you run into those kind of problems. So maybe it's possible on some planet somewhere that there's some very simple form of life. But if we want to find the forms of life that we really care about, that are more complicated and doing interesting things, and we can detect remotely because they're affecting the atmosphere through biogenic gases, then liquid water, I think, is the best way to go. We should start with what we know.
Okay, there are no more questions here, so gives me a chance to ask a question. And I want to get on your testing the habitable zone hypothesis. So you're saying that you measure the atmospheric composition. I would assume that you do that in the infrared. And then I mean, what exactly you mean by atmospheric composition? Do you fix that to a certain molecule concentration, or how are you going to do it?
Well, so in this particular case, for the conventional habitable zone, what we're interested in is the trend of carbon dioxide levels. And carbon dioxide has absorption features in the near infrared, the thermal infrared. So as long as you're in the infrared, you can probably determine and have a high resolution spectrum. Mm-hmm. Then you can use spectroscopy to determine that. Now, it's not necessarily easy because because of noise that you might have and limited resolution. But that is the basic idea as to how you do it. For the rest of the atmosphere, does that matter? Well, it could do, yes, because the amount of nitrogen that's in an atmosphere will affect the greenhouse effect, because its collisions can temporarily cause dipoles. And so if you pump up the nitrogen, you have more collisions and more collision-induced absorption. But that's a bit of a stealth gas, because it doesn't have much of a absorption spectrum that's particularly strong. So we may not know that. So really, there are some other things that can also confound this measurement, such as what the other gases are doing. But if you just take the basic idea that there should be a background trend in this gas, because that's what defines the conventional habitable zone, and that's what people put in their relative models. The question we were asking is, can we just look at that one gas and get a trend? The rest of the composition could be quite interesting. So, with my group, we've written papers on looking for ancient Earth, life on ancient Earth, when you don't have any oxygen. And there we argued that if you can see carbon at each end of the redox spectrum, so methane and carbon dioxide, both of which have absorption features in the near infrared and thermal infrared, then you might be able to infer life existing on the equivalent of an Archean Earth, so Earth before 2.5 billion years ago. So the other gases are important, certainly really important for biosignatures. but maybe we can't detect some of those because they're at small levels, or but CO2 should be a gas which with very good absorption features, because it's such a strong absorber that in principle it's tractable, but you just need a very big telescope and plenty of time.
Got it. Thank you. There is a raised hand. William Ball raised his hand. And Willie, could you give the floor to William?
Hello.
Yeah,
I really enjoyed your talk, although I think it would have benefited from including more British tabloids.
I don't think so.
All the AC talk should have British tabloids mentioned. I wanted to ask you about the James Webb Telescope, because you said that you need this really large telescope in order to test the habitable zone hypothesis. But with the James Webb Telescope, they are planning to observe the atmospheres of planets, especially in the TRAPPIST-1 system. So maybe they can start testing that idea with the Webb telescope. What do you think?
Yes, to some extent. But that's just one system, and that's a pretty unique. Well, I wouldn't say unique, but that's a pretty unusual system, because it's a very faint red dwarf star, and we'll see. I mentioned that that question fairly near the beginning of my talk is are planets in the habitable zone, which are in the habitable zone now, of red dwarfs. Are they actually habitable? Because they didn't used to be in the habitable zone because of this superluminous phase. But that also depends upon whether there's been planet migration in the system. And so I think what we get from James Webb is a glimpse of what we see around red dwarfs, which is the things that it can look at or nearby. But it's going to be just, if you're looking at an elephant, you're just looking at the tip of the trunk. And there's a lot more to the elephant. And what I'm talking about is other stellar types, more Earth-like planets, because we don't, some of these planets in the TRAPPIST system, who knows if they're really Earth-like, we'll see.
Thank you.
Okay, thank you very much. And I think we let David go to give his lecture at the University of Washington, I suppose. Thank you very, very much again for this fascinating talk, and thank you very much for joining us, the audience. Next week, we have a talk by Francis Westall on Is Water and Rock All That Is Needed? Geology, Life, and Habitability. So I'm looking forward to that talk as well, and to you joining us again. So have a good week, and see you next week. Bye-bye.
Bye, thank you.